Okay, so in section 8.2, we're actually going to learn how to solve homogeneous linear systems. So the last time we learned some technology about linear systems, and this time we're going to learn how to actually solve them. Okay, so just to remind you, so this is going to be similar to the case of just one differential equation, and so it's going to look very similar to what you did previously. So before, when we had one differential equation, we assumed that it had a certain form, so we assumed that it had the form e to the mx. In this case, we're going to assume that our homogeneous solution has the form k e to the lambda t, where this is very similar except for k here is a vector. And this is the vector that you actually want to find, so you're going to want to find k, and you're going to want to find lambda. So in the previous one equation system, we only needed to find our m. In this case, we have two things to find. We have to find what lambda is and what k is. So if you've taken linear algebra, then you hear lambda and you think of eigenvalues, and that is exactly what we're going to do. These are going to be eigenvalues, and these are going to be actually our eigenvectors. Okay, so we're going to go through and we're going to see how we actually do this. So then the question is how do we find k, how do we find lambda, such that x equals k e to the lambda t is actually a solution to our homogeneous equation. So if you plug in this into the system, if you actually go in and you plug this into your system, then you can actually derive a lot of different things, and you can actually figure out that you actually get that lambda has to be an eigenvalue and the k is an eigenvector. So to see this, go ahead and plug it in. So on the left-hand side, we're taking the derivative. On the right-hand side, we're plugging this into our system. So when we take the derivative of this part, k is just a constant. So we get lambda k e to the lambda t. And then this side, we just have ak e to the lambda t. E to the lambda t is a non-zero function, so it's on both sides, so we can cancel it. So we have lambda k has to be equal to ak. Rewriting this says that ak minus lambda k has to be equal to 0, so if we move this onto the right-hand side. And factoring out the k, we get a minus lambda I k is equal to 0. This exactly means that lambda is an eigenvalue of a and k is an eigenvector from linear algebra. Okay, so how do you find eigenvalues? So reminding you how to find eigenvalues for a matrix. So you look at the determinant of a minus lambda I. You set this equal to 0. This is a polynomial in lambda. So a minus lambda I gives you a polynomial like lambda squared. A lambda squared plus b lambda plus c equals 0 if you just have a 2 by 2 matrix. If you have a 3 by 3 matrix, you're going to have a lambda cubed term in there. And so basically, when I find this polynomial, that is called our characteristic equation, and the roots of it are our eigenvalues. So you solve this polynomial equation for lambda, and those lambdas that you find are called your eigenvalues. So given an eigenvalue, the next thing that you need to do is find the eigenvector. So the eigenvector is just this k. Eigenvectors are never equal to 0. So it's this vector k not equal to 0 that is the solution to this system. So basically, given lambda, let's say lambda is 1, you plug in lambda equals 1 here. This is the identity matrix. You find this matrix here, and then you solve for the vector that gives this thing times your vector is equal to 0. And then that's called your eigenvector. So we all know that solutions to a polynomial equation can fall into 3 cases. We've seen this time and time again. You can have real roots. So in this case, real eigenvalues. You can have repeated real eigenvalues, just because you can have repeated roots to your polynomial equation. You can also have complex roots, so you can have complex eigenvalues. So we're going to look at each of these cases. We start off with case 1, in which we have distinct real eigenvalues. This is our easiest case. So if you have distinct real eigenvalues, then each one of these eigenvalues have an associated eigenvector to it. So you have the form k1 e to the lambda 1t, or ki e to the lambda it, is a solution to your system. So to find the general solution, you're just going to add all of these, just like we had before. So the thing is if you have distinct real eigenvalues, then you're going to have a distinct eigenvector for each one. You're going to form this solution, and then you just take the linear combination of them, similar to what we did in the one equation case. Okay, so let's look at this one. So we want to find a general solution to this system. The first thing we do is rewrite it as a matrix system. So this left-hand side becomes our x prime. This right-hand side, our vector x is our little x, little y. We take our coefficients off of here, so we have 1, 2, 4, 3. That's our A. So now we need the eigenvalues and eigenvectors for this matrix A. So to find the eigenvalues, we need to find the determinant of A minus lambda I. So this is the determinant. Here's our A minus lambda times our I, identity matrix. So this is 1 minus lambda, 2 minus 0, 4 minus 0, 3 minus lambda. So you want to find the determinant of this. So I take 1 minus lambda times 3 minus lambda minus 8. I simplified this. So when I simplify this, I'm going to FOIL this part. So I have a 3 minus 3 lambda minus lambda gives me a minus 4 lambda plus the lambda squared, and then I had the minus 8. So rewriting all these terms and simplifying, the 3 minus the 8 gives me minus 5. So I have lambda squared minus 4 lambda minus 5. This can be factored into lambda minus 5, lambda plus 1. So we get two eigenvalues, 5 and negative 1. These are two distinct real eigenvalues. So now to find our solution, we need the eigenvectors associated with each one of these. Okay, so let's start with lambda equals 5. So basically what we have to do is we have to solve this system. We need to find K1. So set up the system. So A minus lambda 1 I. So here's our A. Here's our lambda, which is 5. Here's our identity matrix. We want to multiply that by some unknown vector K1, K2, which we're looking for, and set that equal to 0. So here we have 1 minus 5. Gives me a negative 4, 2 minus 0. Here you have 4 minus 0, and 3 minus 5. So this is negative 2, and you're solving this system. So you can rewrite this system in its augmented form, where you don't have to worry about these K1s and K2s. And what you're always going to see is that you're going to always have a row of just zeros in here, because you always have to have at least one free parameter in order to have an eigenvector. So if I add these two, if I take my second row and add to it my first row, I get zeros in the bottom. And then here, I just went ahead and simplified this top one divided by negative 4. So here, that gave me a 1, negative 1/2. This is 0. So we see that K2 is a free variable. And if we look at this, we have K1 minus 1/2 K2 is equal to 0. So K1 has to be equal to 1/2 K2. So to find our eigenvector, let's set K2 equal to something that we like. I set it equal to 2 because 1/2 times 2 gives me just a 1 down, 1 here. I don't really like working with fractions if I don't have to, so I'm just not going to. So this is an eigenvector. If you had chosen K2 equal to 1, then you would have had 1/2 1, which is an eigenvector. That's a different eigenvector. It's perfectly okay. Okay, so now we do this for negative 1. Again, we're going to solve this system. We need our K2. So we set up our A. So we have minus a negative 1. This gives me a plus here. We form this. We're going to have 2, 2, 4, 4. So again, putting it in augmented form, notice that I can take negative 2 times this one, add it to this row, and I get zeros down here. I can divide by the 2's, and I get 1's up here. So K2 is again a free variable because I don't have a leading 1 here. So my K2 is free. This says the K1 plus K2 has to be equal to 0. Solving that, K1 has to be negative K2. Easy choice is letting K2 be 1, so I get this eigenvector negative 1, 1. So we have two eigenvectors, two eigenvalues. the only thing left is to form our solution. So we have our constant times this eigenvector times e to the 5t plus a constant times this eigenvector times e to the minus t. And that's our general solution. Okay, so let's look at a 3 by 3 case. So we do the exact same thing. It's just we're going to have 3 eigenvalues in this case. So we set up our determinant. So here we have a minus lambda I, just simplifying. Notice here that what you have on the diagonal is your original matrix here minus lambda. So here I have -1 minus lambda, 2 minus lambda, -1 minus lambda. All the other ones are exactly your A. So you don't really have to write down this step. You can just go straight to this step. So then again, finding, I'm going to take across this first one. So here I'm going to find the determinant across this. So I'm going to have -1 minus lambda times the determinant of this part, and then -1 times the determinant of the 1, 0, 1, -1 minus lambda, and then I have a 0 for the other part. So basically this is my determinant. I need to find my polynomial. So multiplying this out, so this determinant becomes my 2 minus lambda times -1 minus lambda minus 3. This one's just my 1 times this minus 0. So I just get this. Okay, so simplifying a little bit, here I just fold this part. When I fold it, I had a plus lambda and a minus 2 lambda. That gives me a minus lambda inside. I have this minus 2 and a plus lambda squared. I can simplify a little bit farther. So here I have lambda squared minus lambda minus 5 inside. Notice that -1 minus lambda is in both of these terms. So I can factor it out. So when I factor it out of the first term, I'm left with lambda squared minus lambda minus 5. When I factor it out of the second term, I'm left with a -1. The minus 5 and the minus 1 give me a -6. Finish factoring. I can factor out a negative here, so this ends up being lambda plus 1. This factors into lambda minus 3, lambda plus 2. So I get 3 different eigenvalues. I have -1, 3, and -2. So again, for each of these, we need to find the eigenvector. So starting with lambda equals -1. Here is our A minus lambda I, so that would be plus our identity matrix. I find the augmented system. This gives me 0, 1, 0. Here I have 1, 3, 1, and 0, 3, 0. So I want to solve this. So I'm going to flip this row to the top because this is where my leading 1 is. And then I switch these, so I switch the 2 top rows. Here's my leading 1. And then I can get rid of the bottom because I could take -3 times this row plus this row gives me all zeros down here. So I can also take -3 times this row and add it to this one. So if I do this, I can simplify even farther. So that would give me a 1, 0, 1, 0 here. So I get that K3 is my free variable. K2 has to be equal to 0, and I have K1. I can simplify this to be 0. So I have K1 plus K3 equals 0, or K1 is negative K3. So I just don't want to choose that free variable to be 0 because I want a non-zero eigenvector. So I let it to be 1. So I get my K1 is -1, my K2 was 0, and my K3 I had let to be 1. So this is my eigenvector. Doing the same thing for lambda 2 equals 3. So again, this is my system here. So simplify, I have -1 minus 3, so I'm going to get a -4. 1 minus 0, and 0 minus 0. 1 minus 0, 2 minus 3, 1 minus 0. 0 minus 0, 3 minus 0, and -1 minus 3. So it simplifies to this. Again, I want to solve this. So I switch my top 2 rows because I already have a leading 1 here. I can now take this row times 4 and add it to this one. So if I take this row times 4, -4 gives me the 0. -4 plus 1 gives me -3. 4 plus 0 is the 4. And I left this one the same. Notice here that these are the exact same, so I can add them together and get all zeros here. And then I can divide this one by -3. So this gives me -4/3. So multiply this whole entire row by -1/3. And then the last thing I can do is I can add these two rows together to get rid of this -1. So then I end up with 1. When I add this together, I get 0. -4 plus 1 gives me a -1/3. So I have this system. My K3 is my free variable. My K2, when I move this to the right-hand side, is equal to 4/3 K3. And my K1, move this to the right-hand side, is 1/3 K3. So letting K3 equal 3, then we get the eigenvector. So K3 is equal to 3, my K1 is equal to 1, and my K2 is equal to 4. The last one that we need is we have lambda equals -2, so we have this system. We go through the exact same process, form our augmented matrix. Reduce, so take -1 times the first row plus the second row. This gives me this system. Take the -1 times this one and add to the last one. I get my zeros down here. I can simplify this into by multiplying by 1/3 here. And then take -1 times this and add it to that one. I get my reduced system. So having my reduced system, I have the K3 again as my free variable. K2 is -1/3 K3, and K1 is +1/3 K3. Setting K3 equal to 3, we have our third eigenvector. Okay, so now we have 3 eigenvalues, 3 eigenvectors. They're all distinct. So we can form our general solution by saying we have a constant times our K1, e to the -t, plus the constant times K2, e to the 3t, plus a constant times K3, e to the -2t. Okay, so now for the second case. Second case, we have repeated real eigenvalues. So we're going to assume that our eigenvalues are repeated with multiplicity m. So there are 2 cases. One, you could actually have m different independent eigenvectors. And in this case, if I have different independent eigenvectors, then I have K1 e to the lambda t, K2 e to the lambda t, Km e to the lambda t. All of these eigenvectors are multiplied by e to the lambda t because this lambda is the exact same thing. There's only one eigenvector, then this is more complicated, and I'm going to show you an example with that one. Okay, so let's consider this system. So we have this system of 3 equations, 3 unknowns. So we can write it in matrix form. So the first thing we have to do is we have to find our eigenvalues of our matrix. So we look at the determinant of A minus lambda I. Again, we take our matrix, the only thing on the diagonal, you have these minus lambdas, and everything else looks just like your A. Simplifying, I have 3 minus lambda times this determinant. Going across here, I have minus the -1, gives me the plus. And I have, when I got rid of this first row, middle column, I have this. And then -1 times this part of my matrix over here. Simplifying, so again, all I'm doing here is multiplying out my determinants and want to get it into a matrix. Notice here that I have a 2 minus lambda, I have a 2 minus lambda. Here, if I factor out a lambda, I have a lambda minus 2. So I can say this is 2 minus lambda. So here, this is a +1 that gives me that +2. Here I factored out a negative lambda, so this gave me a lambda squared minus 3 lambda here. And then I can factor this a little bit farther. Notice this gives me lambda equals 2, this gives me lambda equals 2, and this gives me lambda equals 1. So we have lambda equals 2 shows up twice, so it has multiplicity 2, and lambda equals 1 shows up once. So for lambda equals 1, let's just go ahead and solve that one because that only shows up once. So we should get one eigenvector for that. So when I do this, again, I'm going to solve my system A minus 1ik. So I'm subtracting 1 off of my diagonal, and my right hand side is equal to 0. So again, I simplify, I switch my top 2 rows. So I have this, and then I'm going to get rid of this 2 and this 1 here. So multiplying by -2 the top row and adding it to the second. -2 plus 2 gives me 0. Negative 2 times 0 minus 1 gives me negative 1. Negative 2 times negative 1 gives me 2 minus 1 gives me 1. Again, multiplying this one by negative 1 and adding it to my last one. Negative 1 plus 1 gives me 0. Negative 1 times 0 minus 1 gives me negative 1. This gives me plus 1 plus 0 gives me 1. And then I can add the last two rows. I get that row of zeros like I should. So this tells me I have a leading one here, a leading one here. I do not have a leading one in my K3 term, so it's my free variable. And then this one gives me K1 minus K3 equals 0, or K1 is K3. This gives me K2 minus K3 is equal to 0, or K2 is equal to K3. So setting K3 equal to 1, I just get a vector of 1s. Okay, so now dealing with the lambda equals 2 case. So again, I'm looking at a minus 2i times k equals 0. This is my augmented form. Notice here that I have a leading 1. If I multiply this by negative 1 and add it to my second and my third rows, it gives me this. So I have a leading 1 here for my K1, but I don't have a leading 1 for my K2 or my K3, so both of these are free parameters. I have my K1 minus K2 minus K3 is equal to 0, or K1 is equal to K2 plus K3. So we have two eigenvectors. So we have, if K2 is a free parameter, let's say K2 is 1, then we're going to have, if K2 is 1, we're going to have 1, 1, and then K3 is 0. So now let's say K3 is 1, K2 is 0. So if K3 is 1, here we get the 1. So K2 is 0, and K1 is 1. So we get two eigenvectors associated with this lambda equals 2. So now we have lambda equals 1 with this eigenvector, lambda equals 2 with these two. So we do the exact same thing. The only thing that you're going to see is you have e to the 2t and e to the 2t here. But we still have our general solution. Okay, so now if it's a repeated eigenvalue and it only has one eigenvector, then basically the way that we find our first solution is the normal one. It's that eigenvector e to the lambda t. Then our next solution, we're going to actually have a different vector times t e to the lambda t plus a different vector e to the lambda t. And then we keep on increasing. So instead of t, the next one is going to be t squared over 2 factorial plus t e to the lambda t plus e to the lambda t. The t cubed over 3 factorial e to the lambda t plus t squared over 2 factorial e to the lambda t plus t e to the lambda t plus e to the lambda t. So you're going to have this form. And you go for however many m's you have multiplicity for. Okay, so let's look at this. If lambda has multiplicity 2 and you found one eigenvalue, then you know what one solution is. So you've only had one eigenvalue, you have one solution for that lambda. So this is it. So then the second one is going to be, your second solution is going to be kt e to the lambda t plus some p e to the lambda t. Notice this is the exact same, just with a t. So I take this one, multiply by t, and I have to find a new p. Well, we already found k by setting up this equation. The way that you find p is, instead of a k here, I have p, and my right-hand side becomes k. So again, I find my eigenvector. I find my eigenvector just like I always do. That gives me one solution. Then I set up the second system. I already know what k is. I don't know what p is. I need to find p. So I find p, and then my second solution is what my original k was, times t e to the lambda t, plus my new vector p e to the lambda t. Okay, so let's do this with the example. Okay, so here is our system of differential equations. So we need to first find the eigenvalues. So again, we take away lambda from the diagonal. All the other entries stay the same. So when we do this, we have 3 minus lambda times negative 3 minus lambda plus 9. This gives us lambda squared equals 0. So we have lambda equals 0 with multiplicity 2. So to find the eigenvalue for lambda equals 0, again, we do the exact same thing as we did before. We set up our system. So here this is a minus lambda I, and our right hand side is 0. So if I multiply by negative 3 times the first one and add it to the second one, I'm going to get zeros down here. And here I can just go ahead and multiply by 1/3. This gives me a 1, negative 1/3. So my K2 is free. My K1 is 1/3 K2. So again, to make my life easier, I'm going to set K2 equal to 3 so I can get rid of the fractions. And this is my one eigenvector. But lambda equals 0 has multiplicity 2. So this is my one eigenvector. I need to find my next one. I already have my first solution though. My first solution is going to be my K, e to the lambda t. E to the 0t is just 1, so this is my K, e to the lambda t. Okay, so the second solution is going to be given by this. So I need to find P. I already have K. I'm going to put P here instead. So what this left-hand side is the exactly a minus 0I, because my eigenvalue was 0. But now my right-hand side is my K. So here's my K. That's what my right-hand side is here. So now I want to solve this non-homogeneous, so I don't have zeros over here. But I go about doing the same thing. So if I multiply by negative 3 and add to this one, negative 3, I'm going to have negative 9 plus 9 is 0. 3 minus 3 is 0. Negative 3 plus 3 is 0. So this whole bottom part becomes zeros. That's what you should see. Then multiplying by the top by 1/3, I have 1, negative 1/3, 1/3. So these are correspond to P1 and P2 now. So my P2 is free, and I have this equation that P1 is 1/3 plus 1/3 P2. So P1 minus 1/3 P2 is equal to 1/3. So I get this equation. So here I let P2 equals 2 because I know I can get 2/3 and 1/3 and it makes my life easier. I don't like fractions, so this is my P. Again, everybody could have a different P in this class. Okay, so my x2 is going to be kt e to the lambda t plus p e to the lambda t. So this was my k, t, e to the lambda t, and then my p, e to the lambda t. So again, e to the 0t is just 1. So here this ends up being 1/3 t plus 1/2. So we have two solutions. And then once we have our solutions, then our general solution is just a linear combination of those. Okay, so if lambda has multiplicity 3, then we find, and only has one eigenvalue, we find that first eigenvalue the same way. And here's our x1. We find the second one by saying, second solution by setting up this, where our p here goes here, where the k was, and our right-hand side becomes k. And guess how we find our third one? Our third one, now the p becomes the right-hand side, and q is here. So this is how we find our third solution. So each one goes up by 1 and is divided by that factorial. So t squared over 2 factorial. Okay, so here's our matrix. Let's find our eigenvalues. Again, we want to find the determinant here. Go through just like what you always do. This one's simple because we have zeros across here. So then this is our system. We factor it out completely. And what we get is we get lambda equals 1 with a multiplicity of 3. Okay, so let's find the eigenvector associated with this. So we set up our system to find the eigenvector. So again, this is our a minus lambda I. Our lambda is 1 here. So this becomes, we already have that row of zeros, which is nice. We have this term and this one. Simplify it. So I basically moved this to the bottom row, moved this up, multiplied by 1/2. That's why I get this top row. This one stays the same. I have a leading one for my K1, leading one for my K2. My K3 is free. So I just simplified it a little bit more. K3 is free. So what I get here is my K1 is equal to 0 and my K2 is equal to K3. So letting K3 equal 1, I get 1 eigenvector. And then the solution associated with that is my eigenvector times e to the lambda t. Lambda was 1, so this is just e to the t. So the next one, I have my p here. I have that k that I just found on the right-hand side. So this is still my a minus lambda I. This is my k. So I again simplify. So I move this one to the top row and multiply by 1/2. So that gives me this equation. This one's becomes my second row. And then I can multiply the second one times negative 1/2 and add it to the top. It simplifies. So to find my p, my p3 is free. This equation says P2 minus P3 is equal to 1. So that means P2 is 1 plus P3. This one says my P1 is equal to 0. So in this case, I can say my P3 is 0 because that doesn't give me a 0 eigenvector. And so I get this simple eigenvector. It makes my life simpler for when I need to find my third one. Okay, so then this is my solution. Remember, is my k, so this was my original k, t e to the t, and then this is my p e to the t, because my lambda is just t. Okay, now I'm looking for q, and I'm using that p that I got, so this is my p, that's 0, 1, 0. I go and solve this one. Here I have q3 is free. This tells me that q2 minus Q3 is equal to 0, or Q2 is equal to Q3. This one tells me Q1 is 1/2. So here I can let Q3 be equal to 0 because again I don't get a 0 eigenvector. I still have this 1/2 here, but Q2 and Q3 is 0. So my x3, I have my k, that was my original k, t squared over 2 factorial e to the lambda t. This was my p, t e to the t, and then this is my q, e to the t. So always the new one goes with the last. So I have my 3 solutions. To find my general solution, I basically take the linear combination of these. Okay, last one. Complex eigenvalues. So with complex eigenvalues, you're going to have lambda is equal to alpha plus or minus I beta. So let's just assume we just consider one of those. You're going to have alpha plus I beta, and you have its conjugate. So technically you would have these 2 solutions, but we don't like working with complex numbers in our solution. So what we do is with our lambda, we find, since our lambda is complex, we're going to find complex eigenvectors, and so we're going to let B1 be the real part of that eigenvector, B2 be the imaginary part of that eigenvector, and so our solutions are going to be combinations of cosines and sines that have this beta inside, and then e to the alpha t. Okay, so let's work this one with examples. So we want to find the general solution to this system. We first find our eigenvalues. Again, 6 minus lambda, and then 2 minus lambda on the diagonal, negative 1 and 5 on the off diagonal. Multiplying it out, simplifying it, we end up having our roots are 4 plus or minus I. So here our alpha is 4 and our beta is 1. So that 4 plus I is what we're sticking in here to our k. So we have 6 minus 4 plus I, 2 minus 4 plus I. Simplify. I flip these rows because I want to work with a real number up here. So I flip the rows and I simplify. The 2 minus 4 gives me a negative 2. 6 minus 4 gives me a positive 2. So then I'm going to multiply this one by a 1/5, this whole entire row. And then I'm going to multiply it, then I'm going to multiply this all times the minus 2 plus I. I end up getting all zeros down here. Remember, you're always going to get a row of zeros if you've done this right and found the right eigenvalues. So Here my K2 is free, and my K1 is 2 plus I, because we're moving this over, divided by 5 times K2. I'm letting K2 be 5. Again, I don't like those imaginary ones. So my K1 is 2 plus I, and my K2 is just 5. So this is my real part, this is my imaginary part. So real part, imaginary part. So going back to what the form is, we have B1 cosine of beta t minus B2 sine beta t. B2 cosine beta t, B1 sine beta t. So looking at this, we have, so our first one, our x1 is B1 cosine of beta t, our beta is 1, minus B2 sine of beta t is 1, e to the alpha t, so that's e to the 4t. Our x2, we flip these, so we have the imaginary part, cosine of t, plus the real part, sine t, e to the 4t. And so then we can combine this. This is 2 cosine minus sine t here, and then this is 5 cosine, and then they're all times e to the t. And then this is cosine plus 2 sine here, and then 5 sine in the bottom. So we get our solution. Okay, so that is all of how you actually find the general solutions to our linear systems for our homogeneous linear systems. So next time we'll talk about non-homogeneous.